Welcome, everyone, to our fifth and final course of the GMDSI Python Decision Support Analysis Notebook hybrid course. Yeah, so we added this one on because we knew we wanted to dig more into the optimization tools, so PES++ opt and MOU. But we also, like always, really want to open up the floor for any questions on any of the material that we've covered, up until this point. So if we still have more questions about IES, great, feel free to chime in. So, but the homeworks specifically for last week were to go through those opt and MOU notebooks, which there was quite a few and, quite a lot of information. So we wanted to take a moment and open up for any kind of questions people have. We are going to dig a bit more into them shortly, but please raise your hand if you have anything specific you want to get into before we do that. Nope. Okay, cool. Great. Well,
I'll keep admitting people while you're.
Yeah, great. Here. Thanks, Mike. So I wanted to just pull up our trusty reimagined adventure repository that has really gone some places with us. So I think it actually was a pretty good repository name at the end of the day. And you guys did this in the homework, but I just wanted to walk through it again because it is really, it's a, like I mentioned in the last class, it's a lot of reframing of terms, like thinking of things in terms of decision variables instead of parameters, and constraints instead of maybe observations or groups of parameters. But it actually is quite simple to go from an IES run to optimization or MOU. And so I just wanted to kind of walk us all through that one more time, just so, it really kind of sticks for everyone that to move from uncertainty quantification to management optimization is thanks to PES++ and PyEMU. It's quite straightforward. So this is the PEST from all the way through looking at weights and observations, looking at rejection sampling, and then IES. It's that same notebook. So where we ended the last time we looked at this notebook was actually running IES on that prior that we had culled based on some rejection sampling criteria. So in this directory, we have a posterior parameter ensemble that now we can take and actually start to do some management optimization on. So I'm going to do the same kind of objective as what you looked at in the homeworks, because that's just kind of how the Freiberg model is set up currently. It just really only works for looking at balancing pumping and stream flow. So like in the homeworks, we want to just maximize the amount of pumping that we can do, and it's subject to some sort of stream low flow constraint. And so as I walk through this, I just want you guys to think about and try to recall it from the homeworks, what the objective function was and how we formulated that, both, conceptually and in the actual PyEMU coding, what the decision variables were and how we actually implemented those, and then finally the constraint there. So like everything, we want to create a new directory because we don't want to overwrite what we've done so far. So I have this code chunk here where I'm just creating a new simple optimization directory and copying that master IES, the one that has our posterior parameters, into that directory here. We're going to go ahead and load the PEST file from that directory. And just to kind of remind everybody of this model, I'm just going to plot up the Freiberg model here. So remember, we have the SFR boundary condition as the stream here. And the thing that we actually want to make sure we don't have fall below is the streamflow gauge results basically at this outlet point. And then each of these red dots are pumping wells here. And then, so the first thing we want to do is, let's look at what our observation constraints are. So I'm going to open this one up. So let's say the two things we want to have constraints on are that stream low flow. So I've actually pre-coded this, so I'm not live coding for you guys today. But the first thing we can kind of do is just take a look at what we have in our previous pest container ops values. So we have, those failure counts, and we have those incremental flow from the listing file outputs. So, percent discrepancy, blah, 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 everything. But the thing we actually care about here is going to be the SFR. The gauge was what I was talking about, right? So can anybody put, since I'm going to kind of do this like a little bit of a quiz on the homeworks, how you would want to set the constraint for this gauge to make sure that we don't have it fall below that specified low flow value. Let's just say that value is 750 cubic meters per day. What's the main thing that you need to do in this observation data section to put that in? And Mike, if you could look at the chat, and I'll go ahead and.
I'm watching the chat.
I'm going to sit here in silence until you guys answer it. So it could get
Someone is typing. Someone is typing.
Yep, there it is. Greater than obs group. Thanks, Savannah. Sweet. So I just have something here, right here. So we first actually want to zero weight everything, because remember, we're moving from IES to optimization. We don't actually want to have any kind of history matching now. So we're going to zero weight all of our observations except for the ones that we're going to use as constraints. And then the value we use for that weight, it doesn't actually matter what that value is. It just needs to be non-zero. So I've put in that low flow constraint here at 750. And then, yeah, Savannah's right. We want to make that a greater than. And PEST is super smart. It sees that and it knows it's going to be a constraint. And then let's just say, because I want to have everybody kind of think back, because we're still talking in just opt space, not multi-objective yet. And we looked at this linear programming example where if you just have constraints and then bounds, you're always going to be kind of just slamming up against either your constraints or your bounds, right? So optimization is going to do the same thing. If we say we want to maximize pumping subject to some constraint, which is stream flow, we're just going to slam up against that constraint, and that's going to be our pumping value, right? So when you're working with optimization, you want to kind of, try to outsmart it, right? And so let's just say, we don't really want pumping to just go to zero just to satisfy a constraint, at some point in time. So we want to kind of give it something a little bit more tricky to try to balance, right? So we want to say here that we want to have pumping should never go below this 2,350 divided by 2 is just some arbitrary value of pumping. And this is incremental, but it's reported for all of the pumping wells. So that kind of stops the PEST plus opt from slamming things to zero to satisfy a constraint or to satisfy an objective, for example. And it gives us basically some amount of pumping throughout the year, but obviously it's going to be greater than that during some parts of the year. So that's it for the observations. And we always want to make sure that we bring that back into our pest observation data section. I've made many mistakes where I do all this fancy stuff and then I never bring it back in. And then, your run doesn't look like what it should look like. Another thing I want to kind of pause and detour on is the fact that we have an IES ensemble, a posterior ensemble. I know in your homeworks you looked at uncertainty, and we're not going to look at that today in this simple example, but often without having to run the full stack for uncertainty, which can be quite costly with optimization or MOU, you can actually inspect your posterior, parameter ensemble and do things like choose a risk-averse realization or risk-tolerant realization, just based on, whatever it is you're trying to avoid or tolerate, right? And in this case, I just want to take the base parse, right, which is that special realization that has sort of smoothest GLM type calibrated parameter set right here. So I can grab that from the parameter ensemble using PyEmu and then set those starting values. And these these only will matter for everything that isn't a decision variable. So all of our properties, which in this really simple example, we're just talking about K basically. So I'm bringing those over. Oh, I have not loaded R yet. There we go. Okay, so now the next question is how or what again do we want to do for the decision variables? Because again, we're talking about we want to optimize pumping for we want to maximize extraction, but then again, subject to these constraints. So what are the decision variables here? And then how are you going to set those? Please put your answers in the chat. And I will just say here. And I guess if we don't know, you can just say, I don't know in the chat.
That's unacceptable.
Yeah. Recall that decision variables are going to be some parameters that we're bringing over, but we're going to, instead of have them be varied within some uncertainty bounds, they're going to be varied within these bounds that we give it that they can actually, a value that they can take on in our, management optimization decision variable space. So I guess I'll take silence as people are not.
Oh, Savannah's back.
Nice, Savannah. Yeah. So pumping rates, yeah, those are going to be our decision variables here. And so it's going to be, we have a number of wells and we have pumping rates for each stress period. So that's going to be, 5 wells times 24 stress periods is the number of our decision variables. And I think that's one thing that we can chat about in a little bit, but there is sort of an upper limit that's recommended of decision variables of basically free adjustable decision variables in an optimization or MOU run most often. And 30 is still in the comfortable range, and you can start to get really, really high. And that's where a lot of the creativity comes in with these problems where you have to start thinking about how we can actually do some dimensionality reduction in these, how we optimize stuff. So again, yeah, we're just looking at all of the parameters here that contain well in them. And so we're going to make each one of those a decision variable par, which I'm just going to give a group name of DV pars here. We're going to reset their lower and upper bounds and their starting bounds. And an important thing too is we need to set that parameter transformation to none. Otherwise you'll get an error. And so this is, basically we're letting, and it's still multipliers here. So we're letting the values of the multipliers range in our management optimization from 0 to 6. And so again, we want to bring that back into the parameter data section. And so the last thing that we need for this, because we've got our constraint, we've got our decision variables, we need our objective function. And so the objective function, right, is again going to be, we want to maximize pumping. So does anybody know one of the ways that we could set an objective function? Just throw it out there. There's basically 2 options. I can tell Savannah's waiting till she's like, I got it. Yeah, if par val is equal to 0, it just means that you're starting out where you're saying there's 0 pumping, but that par val is going to assume different values within the optimization, like within the draws, right? So it'll be greater than that. Is that right, Mike?
Yeah, although that is a good question, but this works, right? So
yeah, it does work. So I could set it to like 2 here if we want it to be, or like 0.5.
Yeah, because when it
Let's just set it to
calculates
1.
the response matrix, right, it is being multiplied. So
Yeah, it's starting
unless
off
you,
with just all 0 pumping, basically.
yeah, that's
Like
interesting.
that first value.
I actually thought that that was a problem. So, but you can set the increment to be additive instead of multiplicative. So when you're basically perturbing a decision variable to see what that impact is on all the constraints to create the response matrix, which is like the Jacobian, you can have it so that it adds an incremental value rather than multiplies. And maybe we did that. In any case,
Yeah, this is
it's a
lifted
good
from the notebook.
question.
Yeah, and
Yeah,
it's possible. And we'll
yeah.
actually get to that one. And since we don't have any answers yet, so we're going to maximize groundwater extracted, and we can use one of these prior information equations. So these are super powerful. You can use prior information as a constraint too, but here we're going to actually use it as an objective function. So what we're saying is for all of those well par names, so it's just a list of all of the well parameter names. So that's, the 5 wells times the 24 stress periods. We're going to give it a name for that prior information equation. We're just going to say this is objective well. And then we're just going to say we want it to be greater than. So we actually want pumping to be, actually, it should be less than, right? Because it's negative.
Because negative, yes.
Yeah, sorry. This is the thing. You always need to think about things in terms of the model directionality, right? So like more pumping is actually a more negative number. So we actually want to do less than for the objective function group. And then this is where we can actually add in the, let me just run that. What Mike was just talking about, where we want to mess with the increments basically, right? So, oh yeah, this is absolute. That's why 0 is okay, because it is an absolute.
That's right.
Yeah, so to go back to your question, Savannah, if we kept it as a multiplier, then that would be not ideal, but and so in IES land, we don't want to have humongous increments, right? Because we're working in gradient space and you don't want to have a huge jump. It's not going to play nicely with the algorithm. But with linear optimization, we want to actually explore as much of that space as possible, but still, we're still kind of subject to that linearity assumption, right? So the idea is that you want to have a larger increment for optimization problems, but not, enormous, because you still need to have some sort of a linearity. Assume that your model is going to behave linearly within that incremental change. How does PEST know that this prior information is the objective function? Oh, that's a good question, and we'll get to that in a second. You actually have to tell PEST. It knows if you give, say, observations, just this group name of less than or greater than, it's smart enough to know that that'll be a constraint, but you actually need to tell it what the actual objective is. And the same goes for MOU. So you actually do have to go in there in the PEST++ options section and say, these are the objectives. So yeah, we're going to give it these new increments. And then this is, to answer that question, this is where we actually tell PEST++ opt the things that it needs to know to actually run this optimization. So first is, since I gave it the group name of DB pars, we actually tell the opt decision variable groups that, right? If I, named it something else, then I would just need to have that name in there. That's just kind of the tie between the two. And then this is that PEST++ option opt objective function. And then I give it that name of the prior information equation. So remember, we gave it that name up here. I'm just going to give it down here. And then we also have to tell it the direction, right? And again, I think we need to call it min. So that's everything we need, and we can actually run optimization. And the result shouldn't look anything different than what you guys had in your homework. Basically, PEST is going to be trying to play around with as much pumping as it can get away with while it can, which, we have this like cyclical recharge and cyclical, or just cyclical recharge, right? So during the wetter periods, it's able to pump basically the full rate. So it slams up against those upper bounds of pumping, especially in the first year. And then in the time period we have that stream low flow kind of coming down close to that low flow constraint that we gave it of 750, then it's going to start turning things off and slamming things down to 0. So, but I mainly just wanted to kind of walk through this just because it is, you just have to think about those 3 things, right? Your decision variables, your constraints, and your objective. And you really, with practice, it'll become quite comfortable to move from an IES to an optimization or an MOU run. But I think this is still, we've only talked about opt up until this point. And, here we can only have one objective, right? And we rarely in the real world, and I was trying to come up with an example that was different from the Freiberg one that you guys did in the homework, and it's actually really hard because, in real world problems, we rarely only have just one objective. Usually there's multiple objectives we're trying to balance. And so that's basically the kind of line of, do I use opt or do I use MOU, right? It's basically, do I have multiple objectives that I need to weigh against each other? And so Mike's going to get into that and the kind of power of MOU. But before we move on, does anybody have any questions about what we just walked through?
Actually, I'll quickly interject. Like one, there are some engineering problems where it's a little bit more single objective. Like for example, dewatering, right? For dewatering for like a building foundation or a mine or something. Like there really is a hard constraint of like the engineering thing cannot proceed unless that water level is attained. So that's a pretty hard one. But when it comes to things like ecosystems or cost and things like that, there's definitely some movement, which is what we're going to move to next. But I'll still leave a moment for questions.
Cool. Guess everyone's good with it.
Yeah, I guess so. Awesome. Well, thanks for the live demo, Katie. That's awesome. Always a good time. Cool. So so exactly what we were just talking about and like Katie brought up is in the real world. Actually, I wanted to bring up here's an example. So in the real world, like for example, if this simple Freiberg problem, like if we're looking at, we want to maximize the amount of pumping that we can attain, but we want to minimize the impact on the stream at the same time. And so in effect, and again, this gets confusing when you have all these negative signs, like for negative pumping is a greater negative number is more pumping. What's minimizing and what's maximizing? I've found that sometimes I actually just flip the signs in the prior information equations, you can flip the sign, or if I'm observing things, I just multiply it by -1 so that, like, for example, I would probably in this problem construct it so that pumping was positive, like a higher positive number was more pumping, and then use maximization. I find when I'm trying to explain it to the sort of clients and stakeholders and stuff, it gets really confusing. So that's just a thought. But in this case, they're both negative. So here's the trade-off curve that in this problem where greater negative values is more pumping and greater negative values is more base flow into the stream. And so those are really competing objectives. What we've seen right now is that there's a strict number of the stream flow as a constraint, and then the objective function is just trying to maximize pumping. But you basically will find one solution to that. But there's a little bit of flexibility here. And the reason I'm showing this is because this illustrates the concept of a Pareto curve. And there's a concept that comes from economics of Pareto optimality. And the idea is that if it's constructed in such a way that the origin, basically both of these things, it's optimal to lower the number. So getting a smaller objective function for pumping and a smaller objective function for stream flow are both desirable conditions. And so ideally you'd find they'd both be like as negative as possible, right? Like some really small value. And so in reality, you end up with this kind of trade-off. This is a really clean trade-off where the curve is pretty much always has the same shape. But one of the reasons that I like to think about this is, what if there was like a real kink in this, like a real change in the behavior? So, if you're looking at, you increase pumping, as you increase pumping, that means you're going down on this axis, you're decreasing the amount of water going to the stream, which means you're going up on this axis. And so that's kind of this smooth trade-off function. But you could get to a point where, you hit a point where the stream goes dry, and then this becomes flat and just goes off into infinity. Or in some cases, it could change in a different way. Combined with the fact that these objectives are inherently in competition, right? Like if you can think of like a regulatory situation, basically there's, say it's irrigated agriculture, for example, like the irrigators are motivated to pump as much water as they possibly can within what they need to be able to irrigate their crops. And then there's an ecological reason for maintaining enough base flow in the stream for ecosystem reasons, for example. But there's not just one answer to that. Like a little bit of decreasing in pumping might actually make a big improvement in stream flow, until you get out to these limbs here, right? Like going from this pumping to this pumping has much less impact on stream flow than it does down here. And similarly, like adding from this amount of pumping to this amount of pumping doesn't change stream flow as much. So there's some point where there's like diminishing returns at both edges of this. And really, we're interested in where these trade-offs are, because in the real world, there's going to be some kind of negotiation about how this thing is going to operate, right? And so that's why MOU, this next technique has been introduced and is so valuable. It's because really you're wanting to look at finding the Pareto optimality. The Pareto optimal point is really defined as where an improvement in one has the smallest decrease in change of the other. And so there's kind of a balance here. If this was a sharper curve, it would be even more obvious. But here, there's kind of a gradual trade-off. So hopefully that makes some sense. But the idea is now we have to use a completely different algorithm now. So the algorithm that is in OPT, the linear programming and sequential linear programming algorithm that we've been discussing so far, can only have one objective. And it also, as Katie showed geometrically, it's kind of going along the lines of constraints and maybe bounds, but that's it. It's pretty limited to where the solutions can be. But once you have this Pareto or this multi-objective trade-off, we use a different algorithm that can actually have a lot more flexibility. And that should basically always be great, except that it's expensive. And if you ran these notebooks, then like they take basically overnight. They take hours to run. And this is with a really simple model. So you can imagine that with a more complicated model, this takes a lot more time. But so just wanted to, got too many things open. I just wanted to go back through, again, just like we did with OPT, we're using the same tool. We're still using PES++, but we've got a little bit more definitions that we need to make. And the reason that we're doing it this way is because all the kind of the pieces of the puzzle that are needed to run either OPT or MOU were already baked into PES. For example, being able to update model inputs, run the model, and look at the outputs in a model independent way. That's such a huge power of PES and PES++. So the fact that was already there, the response matrix that's needed in OPT is so similar to the GLM in some ways. Certainly making that matrix is just like making a Jacobian. So a lot of the mechanics are already behind the scenes, but we do have to have this kind of change in terminology. And so so all of the terms that you've learned so far, like decision variables, are similar to parameters. Constraints are similar to observations. Those all still hold, but we're going to add a couple more when we get into MOU here. And the main reason for that is we're going to start using what's called basically a genetic algorithm or an evolutionary algorithm. And so we've been talking about ensembles. It uses also a concept of like an ensemble, but instead of calling it that, it's called a population. And instead of the ensemble being made up of ensemble members, that population is made up of individuals. And you can start to see this analogy to a biological system, some kind of organisms. And then instead of going through iterations like we do with IES, we're going to go through generations. And then you need some kind of selector, which is now this is the new term. This is basically a way to decide which individuals are best from a population. So the way the evolutionary algorithm works is it takes a population and then it mixes different characteristics of the solutions in that population and looks at what that does to select what is more fit. So this is very much like evolution in natural systems, like survival of the fittest, right? So basically, this kind of mixing of the population is very similar to mating or breeding, like where genetic information from two individuals is exchanged, and the offspring is some kind of combination of those. But we have this objective metric to say, well, what's considered more fit or better, and that gets retained, and the less fit die off, basically. And so, and these are powerful algorithms. They do not scale to a ton of they don't scale to a ton of objectives. And so, really, like we are showing a Pareto trade-off between two objectives. You can have more. There's an upper limit of probably something like 5. And I'll show a little bit of a real world example in a minute, talking about that a little bit. Oh, right. And then, sorry, the generator is basically how does this information of the various individuals get exchanged? And so there's a variety of ways to do this. There's something called particle swarm optimization. There's other ways to sort of take the parameter values effectively of different individuals and kind of move those around. Differential evolution is the default in PES++ MOU. The other thing about these algorithms is they move, so they're expensive because it's sort of like having an ensemble, but in practical situations, the ensembles need to be maybe even bigger than we're using in IES. We talked about 300 to 500 ensemble members in an IES ensemble being reasonable. That's 300 to 500 runs per iteration, right? We often need maybe more than that for MOU to behave well, depending on how linear the responses are. We might be talking, I mean, the last one I ran, I think we started with 850 individuals in a population. And you probably need generally more generations than IES iterations. So whereas IES, we were kind of stressing the idea that you might run, say, 3 iterations, which costs like maybe 6 model run times if you're running in parallel. For generations, we're talking like 50, maybe 100, maybe even more. So it's a very expensive process, which means you really need to put a lot of thought into how you construct things. And I would say, just as a side note, kind of debugging and making sure that the model is behaving the way you think it is even more important here than it is elsewhere, because it's going to be running for a long time and you could really waste a lot of resources, especially if you're paying for those resources, right? And even if you're not paying, money paying by the run, there's opportunity cost for other people using your computers, whatever. Like, it's really important here. You can tie up resources for a long time, as you saw with your laptops. So let's see. So hopefully people ran this first notebook at least, and there's a lot in here, but we can kind of see at the end we get this trade-off, this Pareto trade-off, and that's kind of like the holy grail of where we're trying to go. And that's where you can kind of start to have negotiation with competing parties about what you should do with this. So I made a slightly different visualizer here because I wanted to show a little bit of like how this evolution actually happens. So when we started out the algorithm, we started with a series of with a parameter set, And we ended up with actually only a few individuals in that made it through the optimization for that generation. And that's partly because some of these are infeasible. So infeasible means that it violates one or more of the constraints. And this is very strict. If it violates any constraints, it's considered infeasible. So there was some discussion about, you may have a pretty wide range of, say, pumping rates that you're allowing for your decision variables. But when you make your initial population, sometimes it's a good idea to constrain that quite a bit, just for sampling that initial population, so that you feel more confident that you're going to start out with quite a bit of feasible solutions. But even so, some of those are not going to be feasible. And so we actually have a pretty small range.
Can I just interject, Mike?
Yeah, please.
Kind of following with the whole analogy to IES, it's, we talked a lot about the prior Monte Carlo, and if you have a ton of prior data conflict, there's basically no reason to proceed with history matching, because you are not actually, encompassing observed values with your simulated prior outcomes. And just like that, with MOU, if you do not have feasible members in your population, and ideally a handful of them, there's nothing to optimize, right? If your initial population has nothing feasible, it will error out and give you nothing, basically. So it's that first loop is often one that you have to do quite a lot to try to balance, allowing some wiggle room for your decision variables, but also making sure that you will have feasibility at the start. So that's all.
Yeah, and actually, maybe this is a little bit counterintuitive, especially for people that have used PEST in the past. But with these powerful new tools like IES and MOU, both in particular, ensemble methods, the prior is actually even more important, I think, than in some ways it was in the past. Like, the idea that you can just kind of throw your best, like an initial guess at the problem and get somewhere good. I agree that the same kind of process of reevaluating that prior or reevaluating your initial population here is very important. Cool. And so what I'm showing here is, once we choose which generation we're visualizing, we see those highlighted in blue. All of the sort of viable solutions for all 50 generations are depicted here. And what we see is we're far from this Pareto, what's called the Pareto frontier, right? So this means that these are not optimal. We do see the trade-off that we expect. Like, if we increase pumping, so we go down on the y-axis, we decrease the stream flow, we go up on the right axis, on the bottom axis. That makes sense, but we're very far from this kind of optimal trade-off. And so we can start looking through generation after generation. And even in the first one, this is pretty cool that it jumps out and starts to, based on those initial feasible solutions, it's able to find a whole bunch more feasible solutions in the next generation, just right away. But we're still pretty far from that optimality. And so what we find is we move toward the origin and we kind of spread out in this case, which is pretty awesome. So even after just a few generations, we start to really define solutions that are pretty close to that optimal curve. In this case, after 24 generations, we're not that far off, and there starts to be some diminishing returns here. At 36, we're pretty close, and now we're just like really refining, right, up to 50. We could keep running, but this is, the nice thing about simple synthetic problems is, it shows us that this is really, we can be pretty confident that we've gone far enough in this case, that probably continuing more and more generations will continue to flesh out that curve, but it's probably not going to move a whole lot more optimal and probably not spread out too much more. So that's actually that's pretty cool. That's a nice thing to know. The only way you can really know that is if you've run enough generations, which is part of the challenge. There are some kind of, horseback guess type rules about how many generations you need based on how many decision variables and objectives. but really at the end of the day, it's challenging to know for sure whether you've converged. But seeing that there's not much change over generations is a good way, kind of heuristically.
And Mike, you're plotting, is it the Pareto archive summary output?
Yes.
I'll just throw that in the chat. So because we don't know, right, when we launch these runs, you'll often want to set like, 100, 200, whatever, some really, really high number of generations which is now your inopt max's generations. But PEST is writing to this Pareto archive summary CSV file. So that's basically your best bet for monitoring it and knowing when, okay, it's converged and there's not that much change between generations, so I'll kill it and free up resources for other people or save myself some money. But that's basically what you want to be keeping an eye on. So I'll put that.
Absolutely.
Yeah. It's like
and also there are a couple columns in that archive summary that are worth noting. One of them is feasible. So there are infeasible solutions that are recorded in that file. So you don't want to keep those, or you don't want to visualize those or accept those as part of the final answer. So that's why there's this little function in here to say keep only the ones that are feasible. And also this NSGA2 is the name of the actual algorithm that MOU is running. And it actually has two different fronts that have slightly different meanings. And without going into too many details about the algorithm, I'll just say that we want the front that's labeled as number 1. Number 2 is important for continuing the algorithm and for evaluating what should happen for the next generation. But at the end of the day, NSGA front should be 1 and feasible should be 1. And those are the ones that you should be retaining for a possible end solution. Cool. So we just have a little bit more time. I wanted to show a quick example of visualizing like a real world problem. So this is a remediation problem I've been working on recently. And so what we see on the left, this is an area where there's remediation pumping happening. The red dots are red wells that are scaled to show how much they're pumping. And the blue wells are water supply wells that are also pumping. And you can see they're intermixed. Like this blue shape is the plume of contaminant. And so there are already water supply wells that are within the plume. So so just saying like, well, there shouldn't be any contamination in water supply wells is an infeasible solution here, right? That basically wouldn't be possible. So in actuality, they're doing wellhead treatment at those water supply wells. But we can start to look at, there are two pretty obvious then objectives that want to be met here. They want to so they're running this pumping system. They're not allowed to change any of these blue wells, any of the water supply wells pumping rates. Those rates are fixed. So the only decision variables here are the remediation well pumping rates. And they're all constrained within pretty tight bounds, actually. And there are some other constraints that get a little more complicated. But so what they're trying, then they need a good objective, right? And one objective is maximizing the amount of contaminant that's captured by those remediation wells. A similar one is minimizing the amount of capture by the water supply wells, right? So if we look at those two, that doesn't really make a Pareto curve, that just makes a line, and that makes sense. So if we're capturing less in the remediation wells, we're capturing more in the water supply wells. And so if the remediation capture is low, then we're going to end up with a lot of water supply capture. And it just follows a line: increase remediation capture and almost linearly decrease water supply capture. So that's not terribly surprising. But if we want to look at this in kind of a Pareto way, what about if we look at the cost of the pumping? So not just the capture, but actually the amount of pumping, and that's an indicator of how, like, you could think of that as the cost, right? So 100% is kind of their baseline, and they could either decrease down around 90% or increase to 120%. And then the color scale here is showing that third objective, which is the actual capture by remediation. So sure, if you pump that at the absolute maximum, you have the lowest water supply capture, and you have the highest remediation capture. But, by decreasing pumping, kind of, even 10% from the maximum, or even getting back toward the first, we're looking at maybe not even 1% change in the water supply capture. So there may be some kind of valuable negotiation here, right? Like there may be a case. In this case, the regulators don't really care what the cost is, and the community doesn't really care what the cost is. It's pretty contentious. So that linear line, even though it's not showing the trade-off like in a Pareto optimal way, is still maybe what all they need to make their decision. But if they want to start thinking about cost, this is a good way to do it. And then here we can just look at what does this mean. So you can kind of see the differences are subtle. But for example, if you go to the maximum remediation pumping, a lot of these red dots are a little bit bigger than they are on the left. So there's just a little bit more pumping happening there. Or we could even decrease it, right? So in this case, some of the wells actually shut off. Some of the remediation wells actually shut off relative to the baseline, but that means you're going to be putting a lot more water into a lot more contaminant into the water supply wells. And so obviously you want to be somewhere in the middle of this. This is after 70 iterations. I'm sorry, 70 generations. So I do want to just show quickly, like a little bit how this Pareto front evolves over optimization generations as well. So, and this started with 800. So many thousands of model runs here. The scale is going to shift a little bit, but you can kind of see how as we go to earlier generations, in this case, we actually have a broader set of runs, but we also have a lot that are farther away from the frontier. And early on, we had some solutions that had this really high water supply capture being allowed and really low pumping cost. But technically that's feasible because we said anything under, I think we said 27% capture was technically feasible, but it's really clearly undesirable. And so it's interesting that as we start to go into later generations, our population almost splits into two different populations. And the one with really high water supply capture just starts to die off. It's really, it can't compete with these other ones that are closer to the origin. So after like the 30th generation, the scale jumps. There's nothing at 27 anymore, jumps down to 23 for water supply. And now we start to really refine around what we think is a truly Pareto optimal front. So the reason it's not quite as clean a front, though, too, is that we do have 5 objectives. So we have water supply capture, we have remediation capture, remediation pumping, and then there are a couple previously a couple wells that are down gradient that are previously don't have any contamination, so those were given weight as well. And then so those are the five objectives. So when we're looking at the front, we can only look at 2 at a time, right? And so really we're, there's other reasons that some of these, if you look at the remediation capture against water supply capture, it still makes a pretty clean line. So it gets complicated when you have more than 2 objectives, but the logic is the same. They're all competing against each other. And in a sense, even though the geometry is difficult to visualize, we have that concept of Pareto optimality even among the multiple objectives. So we're saying you can't improve one without diminishing at least one of the others. That's kind of what the point ends up being. Cool. I think that's sort of what I wanted to show with that. I think we can open it up for questions. We didn't talk as much about the uncertainty. And like it is discussed well in the notebooks. There's just so much to this whole concept of optimization, regardless of that. And as Katie said, one way that we can get to one way that we can handle the uncertainty at the beginning is to just select one ensemble member out of our model ensemble from IES. that is either risk tolerant or risk averse with respect to what we're trying to predict, and then just do the deterministic case like we've just shown. So it's just a little bit simpler to do that. But there are all these capabilities to handle uncertainty in opt and MOU. It's just there's a little more mechanics involved, and that's in the notebooks.
Yeah, looks like we got a question about that. Yeah.
Yeah. Yeah. So basically, the way that, like, stepping back and just trying to explain this in kind of plain language, right? Like, if you're running your model, you know that it's wrong. And it's either, so say that the thing that you're concerned about, let's go back to a case kind of like was in the notebooks where we're trying to pump and not dry up a stream, right? And so we can pump to some certain level, and that allows a stream level that's the trigger, that's the constraint stream level. But really, we know that the model is off. It's either over or underestimating that stream. And depending on which perspective you have, you can, so risk is relative, right, to which outcome you care about more. If you're on the pumping side, your risk is that you're overestimating stream flow, and actually you could get it lower, and you could pump more and have a lower stream flow and still be in compliance. Whereas if you're worried about, if you're on the regulatory side or like the ecosystem side, you may say, you know, even if you say the stream level's at this, what if it's actually lower, right? And so the chance constraints are a way to just shift what we consider to be the outcome from the model, so that we're being either permissive, we're either going to allow a little bit more pumping, which means by assuming that we have a little bit of flexibility in the stream flow, we can accept a little bit lower stream flow within the uncertainty bounds of the model, or the opposite way. Or we're saying, like, we want to be more conservative about stream flow. So even if we're, so we want to restrict pumping even more. And I don't know, Katie, maybe you can give that a shot. It's always challenging to explain that.
Well, and they're tied to the ensemble that we give it, right? That represents uncertainty. And so that's, you know, you basically with PES++ opt or MOU, if you want to consider risk or basically add chance constraints, you would be evaluating not just, you know, in the example I showed, which is a single realization, you'd be evaluating it against the ensemble, right? And so you get a number of outputs for your constraints, you get a number of outputs for whatever it is, you know, for your objective. And so that's basically how you would include it in PES++ opt. And so it is a lot more model runs, right? Because you're not just talking about one realization, we're talking about however many realizations and collecting all of the outputs and then coming up with an optimal solution that satisfies your chance constraint, right? Which that constraint is risk neutral, which would be, you know, 0.5. It's from 0 to 1, up to tolerant or averse, right? With PES++ MOU, it gets even more absurd because now we're talking about a population which is comprised of individuals that are a set of decision variables, right? So they are unrelated to your uncertain parameters from your IES, you know, ensemble, right? But in order to evaluate chance, so you would run your population of individuals where you're varying your decision variables amongst each of these individuals over generations. But you also have to evaluate that against your stack, right? Which is going to incorporate uncertainty from just the remaining parameters in your model. So that's, you can, there's different control file parameters or PES++ options to basically tell MOU how many times you're going to be evaluating that stack to kind of minimize that. But we're talking about, like, you know, like exponentially growing number of model runs. And so I think you know, the risk thing is probably the most, when you're first learning about it, it's one of the more attractive aspects of MOU and opt, because, like, look, I can do this model and do this management optimization and then go all the way and say, we've considered all forms of uncertainty that we possibly can, and we've come up with a solution that has, you know, is feasible with this level of reliability, given these decision variable values. But the reality of how expensive that is computationally, often all we can really do is just pick a single realization, which is what Mike was just showing. And I think one of the things that you can think about, though, is that you want to evaluate, you don't want your decision variables to occupy a larger range than what you evaluated in your IES run, right? Because as soon as you move into a territory of your model that you haven't explored uncertainty of, then yeah, it is hard to kind of bring over any kind of understanding of a risk tolerant or risk averse realization from that. But yeah, in reality, most often we're picking a single one. And then I should say there's another approach you can do if you want to consider uncertainty on your optimal set, which is, so what we've done for a project that it is pretty computationally expensive to run MOU with chance, is to come up with a single realization that we think is, a good starting point, and come up with our optimal set of decision variables. And then you can take that and evaluate it against your posterior parameter set, right? And so it's sort of running them sequentially, but not necessarily together. And so you can, kind of do that iteratively, and it's still going to be cheaper, right? So come up with your best set, evaluate that against your posterior parameter ensemble, and, there you go. Is it satisfying your constraint with a, certain level of reliability or frequency? So I just want to throw that out there. There's options that, can save you a lot of time without going, well, I hate to end this by being like, don't ever run MOU with but we're just trying to give some options basically that you can take and trying to apply this going forward. Sorry, I think I took a long time to answer that question.
No, that's cool. I mean, one other, just following up on that, I mean, another thought is like the uncertainty that we're characterizing through our parameters of the model is really important, and we've highlighted how valuable that is. But often in these management situations, the changes due to, say, you're going to assume like higher or lower recharge due to, climatic variation going forward, or like a really big change in pumping, or a really big change in land use or something like that. Often the differences based on like those management aspects and future conditions can dwarf the uncertainty that we're, the whole range of uncertainty that we're calculating just due to the parameters in the history matching time. So sometimes it's still really valuable, but it is also worth kind of considering the how much is the system changing, like in the bounds of the uncertainty that we're characterizing in IES versus like with a future condition. And sometimes the future condition is so different that's actually way more important. Sometimes, not always. It depends on the question. But I guess the maybe the point, like both of us maybe throwing cold water on the uncertainty, is really that it's important to think about what matters. And this is all a computational cost, right? So it's just valuable to kind of do some thought experiments before you start off on a project, and think like, is the parameter uncertainty going to matter, like relative to the changes that are likely to be made to the system? And if the answer is yes, then you got to do it, like, or you should really do it. And if not, then you can kind of think about scaling back. Francisco had a question, which is interesting. So looking at incorporating possible failure, and like if there's a certain quantified % chance that you're going to contain the plume given a certain well or other wells fail, the only way that I can think of that you can really evaluate that is to simulate the system with that well failing, and sweep across the parameters, or do the optimization with that well, not active, and then look at the results, the probability of whether you contain the plume without it. But you sort of have to do, I think you have to basically evaluate this with and without any well that you want to evaluate possibly failing. I don't think that there's a way that you can put that into the loop unless you make that failure something that is like parameterized, like basically allow it to shut off with some with some probability in your prior sample. But I think that might not really be possible. I think you basically have to evaluate the percent of capture, the percent of containing the plume with and without the well and compare the difference. I think that's probably how you'd have to do that.
Thank you.
Yeah, it's a good question though. That's a great management issue, right? Like if you're that's something that someone's going to want to know.
Yeah. I was thinking about, because you don't know if the well is going to fail like at the first year of the operation or at the 10th year of operation. So it could be nice to incorporate that chance into the optimization problem, but I don't know if it's feasible.
Yeah.
Yeah,
I'm trying to think how you could do that with decision variables.
Well, I think you could have another variable that is like on or off, like is this variable, or is this well on or off, and just have it, with some probability sample like it would be kind of a binary variable, which we don't really handle all that well, but you could sample it with some probability in the future it turns off. But the problem is, I think then the whole optimization run would have to be repeated for different scenarios of that well coming or going. So I feel like you'd have to step back and just simulate it with and without. But yeah, that's a good question. I'm gonna have to think about that.
Yeah, thank you.
Yeah.
Well, it looks like Herman is typing. So happy to take another couple questions. Bye. Yeah. Configuration, pretty straightforward. Yeah, it's not hard at all. Runtime, like buy a bunch more computers.
Yeah. Exactly.
Sorry, the runtime is pretty much, I would say, exponentially longer, or multiplicatively longer. I mean, it's going to be like, an order of magnitude more hours, most likely.
In terms of configuration, you're just adding more objectives to it, and then a couple more, parameters that you have to set for, the number of generations, your population size, things like that.
Right, and constraints still have the same meaning in MOU too. Maybe we didn't highlight that quite enough. Like feasibility, the feasible space of the solution is defined by constraints that can't be violated. So, like in the example I showed, we had all kinds of constraints, including things like 3 pumping wells are going to 1 injection well, and that is being treated, and that treatment system has a capacity. So the sum of those 3 remediation rates can't exceed the treatment capacity. There's a bunch of those. There's other things. We had constraints that you can't flood basements. So there's all kinds of So you can maybe add more constraints, but other than that, no, it's pretty much the same setup logistically, which is really powerful. So you should be able to switch between the two if you can, accommodate the amount of runtime. Good question.
Yeah, and I would say, so Mike mentioned something around 5 objectives is probably where you'd want to top out. The same for decision variables. I've heard Jeremy mention like 100 is kind of the max that you'd want to get to. So when you start talking about specifically the remediation thing, where we're talking about optimizing pumping rates for different wells or locations over time, those decision variables can really balloon. So that's where, you have to start thinking about problem dimensionality in ways that you could kind of get around that. Because you don't want to have like 500 decision variables. It's that you just, the population size and the computational cost of MOU would just be infeasible. But constraints, go for it. But the idea is that you don't want to constrain yourself out of feasibility. So
right. Yeah, and that's another thing that's back to, like, I guess if you take anything away from this 5 weeks together, hopefully this idea that like reality checking your problem and running, looking at the prior is so important. Like you can assign feasibility that the model is incapable of attaining. Like you could say, like, the water level can't go below some level, and it's always below that level given your decision variables and parameters. So it's really valuable to make sure that you're assigning things, that you're assigning things within ranges that are in fact feasible according to the model, not just according to what you've been told, like not the parameters of the problem outside. And then also, I mean, all of this stuff with like greater than or less than and the signs like seems kind of trivial, but it's absolutely not. Like I've been bit by that multiple times. It's just like, make sure that you're going the direction you think you are, make sure that things are labeled correctly. And it's worth a lot of evaluation there to save yourself like heartache and trouble going down the road.
Yeah, actually, in the example I was just going over, I realized while you were talking, Mike, that I got it wrong. Like I got it double wrong. So we're trying to maximize pumping, right, which is a larger negative number, but the actual thing that we were maximizing was the multiplier on it. So we did want to get a greater than and a max. So like that's the other thing that can trip you up, because if you're not working in absolute rates and you're working in multipliers, it's a multiplier of a positive number on a negative pumping rate. So yeah, I fully give 2 thumbs up to what Mike was saying. Just check your signs and your greater thans and less thans like over and over again. Any other questions?
I don't see any little dots.
Nice. Well.
Oh, Herman's coming back.
Oh, nice. This is a multi-part.
All right. I mean, if you have already, calibrated a model and you're just wanting to you're basically running a Monte Carlo around those optimal values, then you wouldn't run all of IES. You would just run what we've been calling the prior. But you would need to, if you've done that, if you have estimated parameters through a different process and you feel like they're optimal and good, but you want to have a quantification of the uncertainty around them, you just have to give a feasible, logical range that they can vary, and then run IES with not max -1, right? Like just run the prior. If you think that maybe, I mean, you could also run the whole IES process from that starting point. It might refine those a little bit. It not only changes the values, the actual parameter values, but it can also tighten their ranges, right? Like if you're learning from the observations. So, and I know some people like to do this. They like to run sort of pest in the GLM configuration to get starting values for IES. I don't end up doing that most of the time because I usually have a lot, like just too many parameters for that to be practical. But that's a totally defensible approach to mix the two that way. But basically, you're treating that optimal parameter set as your prior, and moving from there in that case.
Yeah, and something to think about is that if that's the sort of historical period, and then you're wanting to actually do uncertainty quantification for the predictive period, then even if that's an optimal parameter set for the historical, right, you want to give some uncertainty for that honors the fact that we have no idea what recharge is going to be like, in the future, particularly with non-stationary effects, things like that. So I think that's another common one, is to kind of separate out the kind of historical history matching period and then the predictive.
Yeah, great point.
But yeah, just run a prior. If you take anything away from this,
yeah, run the prior.
Prior.
When in doubt, run the prior.
Yeah. Well,
awesome.
Yeah, I mean, this has been really fun. Thank you guys so much for joining along, and we're going to send along with the recording a survey of.
I just
oh,
stuck
yeah.
it in here as well.
Oh, cool. Sweet. Yeah. So we'd really appreciate it if you guys took the time. This is the first, but it won't be the last of these sessions. And so, we'd love to improve upon it based on y'all's experiences, and don't be a stranger. Feel free to reach out at any point in time in the future with questions or on the discussions.
Yeah, and again, part of our motivation for those discussions is that they'll hopefully be searchable if people are just, out in the Googles, like PES++, how do I, set my objective function or whatever. Hopefully things, the more that those discussions are used, they're out there in the world. So hopefully they'll be searchable. So, yeah. So again, yeah, thanks a lot. This has been really fun.
Great. All right. Well, see you guys around.
All right. Take care, everyone.
Bye.